Thank you, Fraser. Thanks, Katie, and thank you, Byron Graham, for the previous session. I'm just getting my screen share set up here, and we will kick it off. Okay, and I believe everybody should be able to see my screen.
You can see it. Thank you.
Awesome, thanks, Fraser. So in my session, I will concentrate specifically on PANOS SD-WAN concepts and details, and some of the configuration elements. I'm currently working as a professional service engineer for Palo Alto Networks, and have been focused on PANOS SD-WAN as well as SASE, mainly Prisma Access, for the last 2 years or so. So when talking about PANOS SD-WAN, right? Usually we start with what's PANOS SD-WAN, and you know, we get these great guides, and basically it says, you know, our PANOS SD-WAN is a virtual WAN architecture which allows for grouping of multiple physical transports, and then it uses software to intelligently route traffic across those transports based on your business requirements or application prioritization. But really, what PANOS SD-WAN is intelligent path selection, to put it in easy terms, right? So we basically can intelligently route applications based on path quality, source destination IPs, source destination subnets, even specific user groups. Also, another thing important to remember about PANOS SD-WAN, that it is just an overlay to your existing PANOS functionality. So from the functionality perspective, your firewall continues to function as is, right? So your security policies, NAT, QoS policies, decryption, application overrides, authentication policies continue to function normally as is, as well as your global protect and everything else. Basically, PANOS SD-WAN is just added as an overlay on top of it. So from that perspective, right, basically PANOS SD-WAN functionality has stayed the same. The three things that were added as a part of the PANOS SD-WAN logic are the three selections we see here. So path metrics, so capability to measure latency, jitter loss, and then basically capability to select path selections and then dynamically change those paths if there's a path degradation. As the PANOS SD-WAN was added in the 9.1 release, there were a few new constructs that were introduced within the firewall and panorama configuration as well, that you may have seen but have not you know, checked or utilized in the past. But basically, these new constructs are SD-WAN interface profiles, SD-WAN virtual interfaces or WIFs, SD-WAN path quality profiles, SD-WAN traffic distribution profiles, and SD-WAN policies. And then the last thing that was introduced for management and orchestration of this whole functionality was Panorama SD-WAN Plugin. So in the next few slides, my goal is basically to go over each one of these new elements. We'll kind of address its functionality, what it does, and then as we get closer to the end of our session, we'll do a PANOS SD-WAN demo and actually look at this functionality in a SD-WAN lab with two different clusters set up, basically. So when we talk about SD-WAN, the first thing we always start with, from the configuration perspective and from setup perspective, are always going to be tags. And you guys are familiar with tags. You've seen them before. They're exactly the same tags that were in there previous to SD-WAN and after SD-WAN. But basically, they're free form entries that you that you create, and basically you can assign them through a few different elements in the SD-WAN configuration. You'll see them referenced in SD-WAN interface profiles, as well as SD-WAN traffic distribution profiles. But they're used to identify common link types and links in SD-WAN interface profiles. So basically, you can use these to identify your primary ISP circuit, your MPLS circuit, your LTE circuit, or your satellite or microwave circuit, for example. In my case, this is actually a screenshot from my lab. So we actually have just the 3 separate ISP providers for this specific location that we'll be looking at in the lab. The second construct that was introduced was the SD-WAN interface profiles. So the SD-WAN interface profiles define the link types, and then they also reference the link tags that we previously created. They'll reference upload, download, speeds of the link, as well as what type of path monitoring profile we'll have. And we'll kind of reference these in just 1 second here in the next slide. But basically, once you configure this, this SD-WAN interface profile, that link tag and that profile is used in traffic distribution for path selection ordering. Few other things that we have here, and actually I'll touch up a little more on these side. But basically, once we select these baseline settings here, right? So our link tag, in this case, my SD-WAN ISP WAN, our link type, which is currently set to Ethernet, but we actually have 9 different link types available. And again, reference in the next slide. We save this profile, and then this is basically the profile we reference under the Ethernet interface or sub-interface when we enable SD-WAN, which then allows us to add it under the SD-WAN tab here under the interface setup. I'll touch up on a few more of these things from the probing frequency and some of these other settings in the next slide as well. So we'll just tap on this. So from SD-WAN profile or SD-WAN interface profile link types, we basically have, I believe, 9 different link types that we can assign here. So we have ADSL, cable, Ethernet, fiber, LTE, MPLS, right? You guys can read them all. What's important to remember, even though there's 9 of them, they're actually split into 2 different link classes, which you won't see referenced under the interface profiles, but basically they're split into either a public or a private link class. So what that means is basically depending on what link class and link type we pick, plugin is going to, the SD-WAN plugin is going to determine how to form tunnel peers. So basically any public link class, including Ethernet, cable modem, ADSL, will form a tunnel peer to any other public link class. So basically fiber will form a tunnel to Ethernet as well as cable modem, as well as Wi-Fi or other defined link type. As far as the private link types, so in this case, MPLS, microwave radio, or satellite, those link types will only form tunnel peers to other links defined as that link type. So MPLS will only form peers with other MPLS defined link types. Microwave will also form peers with other microwave or radio defined link types. And then satellite will also basically only make tunnel peers to satellite link types. Another thing that the link type itself affects is the default method of path monitoring. So this is basically just the default setting, but it can be overridden. But what this means is, and I'll just switch back real quickly to this previous slide to reference it here. We have 2 different path monitoring options, one being aggressive and one being relaxed. Relaxed will be the default setting on usually meter type links. So you can see it here on LTE, 3G, 4G, 5G link type. And it's also a default setting for satellite, which can be overridden if needed. But basically, what these settings say is when configured to use aggressive mode, we send probe packets at a constant frequency of 5 probes a second, so every 200 milliseconds. When we use the relaxed mode, we send probes at a frequency of 5 probes per second for a duration of 7 seconds, and then basically pause based on this probe idle timeout. And then once that timeout expires, we continue with the 5 probes per second for a duration of 7 seconds, basically. The reason we do this on some link types is usually because if you have an LTE link type or 4G or 5G link type, you actually may have a limited data pool shared between all your sites. So rather than probing constantly at 5 probes a second, so every 200 milliseconds, we do a probe set and relax for that minute by default, or we can set that to a higher idle timeout as well if needed. But basically, we stop probing during that time and rely on the previous set of data that we have. And the reasoning for this is if you leave the probe frequency at the aggressive mode, the probing itself just on a single link, so probing on one tunnel back and forth, will use anywhere in the neighborhood of about 200 meg to, 250 meg to about 300 meg a day per link. So just this is not a published doc anywhere, but I've set up some monitors and actually been paying attention to this. And on the LTE link where you may have only 2 gig of data shared pool, that may exhaust your pool fairly quickly. But so basically, after we configure the link tags right, the next step is the SD-WAN interface profiles, where we then assign those link types. Once we have our SD-WAN interface profiles configured and we have them assigned to SD-WAN interface, this is basically what tells plugin, SD-WAN plugin within Panorama on one interface that should participate in the SD-WAN overlay and how it should build tunnels, again, based on those link types, again, that we specify under the interface profile. And this is the slide we've seen previously. So the third concept that was introduced with PANOS SD-WAN was the SD-WAN Virtual interfaces, or SD-WAN VIFs. And these are the interfaces, and they can be basically configured to contain either SD-WAN physical interfaces, like this one, SD-WAN DIA VIF, which you will see for your local DIA internet offload, or they can be configured to contain IPsec tunnels, IPsec tunnel interfaces as a group members of all the same type, right? So basically IPsec tunnels to the other site. And I have a small example here for one of my sites. We basically have SD-WAN 901, which by default is always going to be your virtual interface going out to the internet. And then SD-WAN 902, in this case, this is my interface with all the available tunnels that's connecting to the hub device in this case, and you can tell it by zone to hub, which we'll also talk about a little bit later. But basically what this allows you to do is it provides a layer 3 virtual interface to be used in the IP forwarding table as a destination interface. And then it decouples that underlying physical interface or tunnel from the layer 3 IP forwarding decision. So basically it relies on that WIF for all the forwarding. Also, as far as these SD-WAN virtual WIFs, any members of that WIF that's going between 2 Palo Alto firewalls will have path monitoring probes going end to end. So basically within that WIF between 2 firewalls, we will have path monitoring set end to end from both ends. So basically we'll probe from both ends, and we'll rely on those probes, which we probe again every 200 milliseconds for latency, jitter, and packet loss. For the DIA VIF, we actually only probe to the next stop, which is usually your default gateway. So your ISP provided IP or your MPLS provided IP. However, to get around some of those limitations, we've introduced some additional measurements that allow us to basically monitor past that first hop, which is the default gateway. So in some cases, you may need to manually configure these WIFs with physical interfaces or IPsec tunnels, but usually if you use PANOS SD-WAN plugin, these will all be configured automatically by plugin during the SD-WAN provisioning and the cluster creation. And then the next construct that was introduced as a part of the SD-WAN, PANOS SD-WAN, was the SD-WAN Path Quality Profiles, or PQPs. So basically, you will use these path quality profiles for each set of business critical applications or latency sensitive applications. And it's basically one of the key components of the SD-WAN path selection logic, right? So for latency, when we measured latency, we look at the round trip delay for data packets sent between those probes across the SD-WAN tunnels. Obviously, as you can see here, we measured that in milliseconds. And we work from the probing perspective for latency, we work on a 3-probe sliding window. So we basically, anytime that 3-probe sliding window goes across this threshold, we consider that path disqualified from the latency perspective, basically, and move it to a better performing path. Jitter is also something that we calculate every 200 milliseconds based on our probe frequency, and we also work on a 3-probe sliding window for that as well. And then for packet loss, we also work, we work on the same probing frequency. However, the sliding window we use for packet loss measurement is usually 100 probes. And basically, the main functionality of the PQP, or path quality profile, is determine if a path is qualified or disqualified, or basically in a degraded mode, right? So it doesn't necessarily have to mean it's down. It just means that we have crossed one of the threshold, and at that point, we're considering that path disqualified or degraded. And the second function of the path quality profiles is determine which path to use when more than one path is qualified to basically take the traffic, of a disqualified path. When we look at these thresholds here, basically they are all considered OR conditions, right? So either one of these thresholds going over that specified limit will trigger a failover of the application assigned with this path quality profile. So it doesn't necessarily have to mean that we have to have all 3 thresholds crossed. Basically, as long as we cross one threshold, we will go ahead and move that application or session to a better performing path. The sensitivity settings here is what we use. By default, you will always have sensitivity set to medium, but these are basically settings that we use if we ever want to change the default behavior of alternate path qualification, right? So by default, when we consider, let's say I have a session failover and I have 2 available paths, right? The way I will assess those 2 available failover paths is I will always look at the packet loss first, then I will look at latency, then I will look at jitter. So if packet loss, if packet loss is within the threshold but better on one link, I will prefer that link with lower packet loss. If I ever wanted to change that order of evaluation, basically I could adjust jitter to high sensitivity, in which case I would always, latency to high sensitivity, in which case I would always evaluate latency first, then packet loss, then jitter. I would say for majority of the cases, and what you will see out in the field, these will pretty much always be set to default settings. The next construct that was introduced as a part of PANOS SD-WAN is SD-WAN traffic distribution profiles. So as a part of SD-WAN policies, where we assign the path quality profiles, which you just previously mentioned for specific applications to basically trigger failover, traffic distribution profiles are used to assign distribution method how we want to distribute that traffic. And then the path selection algorithm basically uses the path metrics, thresholds, and sensitivities as defined in the PQPs to determine how we distribute that traffic. So we have 3 available traffic distribution profiles within PANOS SD-WAN. The first one we have is the best available path. And basically, when using this method, the path selection algorithm uses the PQP exclusively to choose the best path from the list of all these available link tags, right? So if multiple paths are qualified, then basically that path selection algorithm will use the sensitivity values, right, that we've talked about within PQPs to prioritize which metric is used first in the selection process. So you'll typically use best available path when link cost is usually not a factor, right? Or you have like 3 very good links, very qualified links, high bandwidth, high throughput. And you want to basically distribute your traffic across whatever the best available link at the time of session creation is. If a path condition changes on one of these best available paths and that path is disqualified, basically the path selection algorithm moves the affected session to a best qualified path remaining within one of these link tags here, basically. The second method we have is the top-down priority. So let me see, I don't think I have a specific path down. I don't. But basically, if we're using the same examples here, same example as here with these link tags, except we're changing the traffic distribution from best available to top down. When using the path down method, the path selection chooses basically the qualified path that matches the highest priority link tag. So whatever is on top is basically considered preferred. As long as it's qualified, we will send that session down that path. So for example, in this case, let's say all 3 paths are qualified. During the path selection, we will always prefer SD-WAN ISP1. So basically, we will always prefer that path as the preferred path as long as it's qualified. If that path gets disqualified, so we're crossing the latency, jitter, or packet loss threshold, at that point, that traffic will get moved to the next qualified path. So if it's ISP2, it will move to ISP2. However, if ISP2 is disqualified, it will move to ISP3. When either one of let's say that session continues on ISP3 path, right? As soon as one of the preferred paths in the top-down session distribution profile gets qualified again, so it's basically preferred, the session will move from less preferred path to a more preferred path based on the top-down priority. So it's going to move either to ISP2 or ISP1 if both are recovered. And then the third traffic distribution profile we have is the weighted session distribution. Basically, what weighted session distribution sounds like is exactly what it is, right? Basically, it's weighted where you assign a percentage across each link tag on what amount of traffic you want to load to that path. So basically, in this case, if I was to switch this to weighted and distribute these sessions equally across these 3 paths, I could do 34, 33, and 33, right? So that would basically load balance the sessions 34% on 1, 33% on 2, and 33% on 3. One of the reasons that, or one of the places where you usually see weighted session distribution will be, again, with metered links, so LTE or satellite possibly. And one of the main reasons is unlike the best available path and top-down priority traffic distribution, weighted session distribution doesn't actually shift your traffic if there is a path degradation. It will actually only shift traffic to another link if a link goes completely down. So unlike best available path or top-down priority, where if we have a degradation, right? So we for example, cross a specific jitter threshold, the top 2 profiles will move that session to a better performing path. With weighted session distribution, that session will actually stay pinned to that path until that link goes down. So usually you will not see this used for business critical applications or for applications where you have to shift that session dynamically between the links if there is some type of degradation happening. And then the next construct that was introduced, and the last one is going to be under the policy settings or object settings here, is the SD-WAN policy rules. And SD-WAN policy rules are very similar to other rules that we have, security rules, QoS, or policy-based forwarding. In a matter of fact, that they basically do the matching on the same type of source or destination security zone, source or destination IP or address, application or service, or also user. But basically, what the SD-WAN policies don't do is they don't do any type of security controls, right? They're strictly there for traffic directing for SD-WAN traffic. So for example, if something is not allowed by your security policy, right, it will never actually get to the SD-WAN policy evaluation, because if your traffic gets blocked on your security policy, at that point it's dropped. It will never even be considered for SD-WAN policy evaluation. If the application is permitted by security policy and then the application is process goes through the content ID, application ID, everything looks good. Basically, then at that point, if there is a zone match or address match or application match for that within the SD-WAN policy rule, that rule will be evaluated by the SD-WAN policy and then basically distributed based on a specified traffic distribution profile, and then will be treated with path quality profiles there specified if there's a need to trigger that or if there is a need to move that application or that session to a better performing path based on the path quality profiles assigned. One thing that's important is once we have a match on the SD-WAN policy rule, basically the path selection algorithm evaluates each path from that traffic distribution profile against the real-time path conditions. So those probes that we're constantly probing right every 200 milliseconds to determine the appropriate path. Once it determines the appropriate path, there's a couple other things that happen on the back end that basically once we send that session or that flow down the appropriate path, we'll do a few other things like enabling basically symmetric return. So one other thing that SD-WAN policy does is, in order to prevent any type of asymmetric routing, right, we'll by default enable symmetric return on any traffic between two Palo Alto firewalls in the SD-WAN environment. I won't talk too much about these, but there were also, as a part of the 10.0 release, there were a couple of other things that were introduced from the configuration perspective in SD-WAN, SD-WAN link management profiles. They're not, you won't see them a lot, basically, but we introduced 2 additional functionalities from the error correction perspective. So in 10.03, we introduced forward error correction for SD-WAN or FEC. And basically what FEC is a way of correcting certain data transmissions without having to or basically a way of repairing a specific sessions utilizing the parity bits that are attached to each session via this error correction profile. Usually where you will see this would be for something that's, for UDP traffics that are where we won't get a retransmit of a lost packet. So for VoIP or video applications. And you will, one important thing to remember with the error correction profiles is because we are, adding additional load. So we're basically adding parity bits to each packet. error correction profiles will introduce slight CPU load to your firewalls. So this may come into play, with smaller platforms like PA220s, and it may cause some undesired results. The other profile we introduced as part of this is a packet duplication, which is actually a lot more impactful from that perspective, from the over the FEC. But basically, the second error correction profile is packet duplication, right? And what we're doing with packet duplication, we're literally duplicating a path, or we're duplicating one session and sending it down an alternate path, so we can use those packets to basically repair a session on the other end if any of our packets get dropped. Again, you won't see too many of these used, and main reasoning for that is in some of the internal testing, I've found usually that our session shift, within the SD-WAN policy is actually a lot quicker and almost completely invisible to the end user than setting these up. Because basically, in most cases, for any session impacted by jitter or latency, we will shift our session within about 600 milliseconds to a better alternate path. And then another feature that was introduced as a part of the 10.03 release was the SD-WAN SAS Quality Profiles. So if you remember, initially I talked about for the DIA or internet offload monitoring, right? Our probing only went as far as the next hop, which was usually your internet provider modem or switch. SAS Quality Profiles basically give us a capability of monitoring past that first hop and basically monitoring SaaS applications, either via specific URL or static IP, or basically relying on the adaptive mode. And I'll touch up on both on all three of these in just one second. But basically, we have three different profiles or SAS Quality Profiles for SaaS-based application. First one being and I'll just go back for some, but basically first one being HTTP or HTTPS, where we're actually probing a URL. So, you can utilize this for something like Office 365. And not only are we probing to that URL, but we're also looking, in this case, for HTTP, HTTPS, we're looking for the service availability behind that URL. So we'll look for service availability on port 80, 443, 8080, and 8081, basically. So not really what we're doing, but it's kind of an equivalent of running a curl command against that URL and waiting for basically 200K response. Is kind of what it correlates to, but it's not really what we're doing. The second option we have is basically static IP, which is the second window here, or this bottom left window here. And we can actually probe to specific IPs, right? Or FQDNs out the internet. And these are literally ICMP probes that we use to measure response back, either from, as an example, Quad 8s or, could be google.com or whatever the case might be. But basically, we can introduce these to measure past that first hop, right? So it gives us a little better measurements than just relying on our ISP next hop. One important thing to remember with these two SAS Quality Profiles is both HTTP and HTTPS introduce additional overhead as far as probes. You have to take security policies into consideration. So you basically have to allow these probes out via security policies. So to either specific FQDNs or IPs, and then for HTTP, HTTPS, you have to make sure you allow the 8443, 8080, and 881. The third SAS monitoring profile we have is the adaptive profile, and basically this is a built-in SAS quality profile that lives internally within the firewall. There's no configuration setting for it other than selecting adaptive monitoring mode. And what this does is once we actually have a session matching a SD-WAN policy that has the SAS quality profile assigned to it, adaptive mode, if set up on that SD-WAN policy, basically gets activated. And what it's doing, it's looking at the TCP response times within that session, and then we'll use those to measure, any type of latency, jitter, or packet loss within that session. this mode is not, or this adaptive mode doesn't introduce any additional overhead. It literally strictly lives within the firewall, right? So there's no additional configuration that needs to be done regarding this. So basically just select it here, give it a name, assign it to an SD-WAN policy. One disadvantage this adaptive mode is because it relies on those TCP response times, right? It only works with TCP-based applications, so we can utilize it for UDP traffic. So within the SD-WAN configuration, those are the new contracts that were introduced, right? Most of them within 9.1, and then some of these SAS quality profiles, as well as the error correction profiles were introduced with the 10.03 release. The last section that was, or portion that was introduced with PANOS SD-WAN is the SDWAN plugin, right? An SD-WAN plugin is basically your orchestration mechanism for deploying PANOS SD-WAN. You technically, if you really wanted to, you could deploy PANOS SD-WAN outside of the plugin. However, at that point, you're kind of creating all of these elements manually, right? And you're you're provisioning your VPNs manually. You're setting up your routing via BGP manually. If you rely on the SD-WAN plugin, all of that is auto provision for you. So basically, plugin will create your SD-WAN VIFs. It will auto provision all of your IPsec tunnels. It will configure your BGP peers, as well as some BGP redistribution rules, redistribution profiles, and export rules. And it will also add all of the predefined security zones and required interfaces that the SD-WAN overlay introduces. It also, in addition to that, also provides monitoring and reporting capability, right? So 4 portions to the SD-WAN plugin are devices, VPN clusters, monitoring and reporting. Within the devices portion, you will basically onboard all of your devices that you want to participate in SD-WAN. Within VPN clusters, you actually create your cluster. So, your hub and spoke clusters, your full mesh clusters, whichever way you decide to deploy your environment. And then within monitoring, you will have your impacted applications, as well any links that might be impacted. And you'll be able to monitor those in 5-minute intervals and go out back to up to 7 days. And then within reports, it's literally just a scheduled reporting for specific SD-WAN functionalities. And this portion here is just a screenshot of the actual devices onboarding portion where you pick up your devices. So the actual naming is a dropdown that will show all your panorama connected devices. You specify your type here, either hub or branch. The virtual router name is also a dropdown. So any virtual router available on your firewall will have visibility from here. Important thing to remember, you can only have 1 virtual router per firewall participate in SD-WAN overlay. And then you assign your site names, any link tags for DI anyPad functionality, and just a few baseline BGP requirements. So router ID, loopback, ASN, as well as any prefixes from the hub perspective you want to redistribute into the environment. For branch, if you select the device as a branch, basically everything looks almost exactly the same, except the link tag portion disappears, and you don't have to do anything by default from the prefix redistribution perspective. As for branch devices, will automatically advertise any directly connected routes on that firewall. And then just to add a couple of different security zones that the SD-WAN will introduce. These are zone internal, zone to branch, and zone to hub. There's also a 4th zone that the plugin creates, but it's currently not required or utilized for anything, so you can safely ignore it, which is the zone internet. But basically, once you deploy SD-WAN cluster, you will see these 3 zones show up. So your zone internal will be a zone strictly utilized for your SD-WAN loopbacks, which will be used for SD-WAN peering, or BGP peering, I'm sorry. And the only traffic you will ever see going in or coming from this zone will be TCP traffic on port 179 for BGP. Your zone to branch will basically become a your egress or ingress branch on your hub location. So if you have a dedicated hub, the zone to branch will become your egress zone for any traffic going to the branch, or ingress zone for any traffic coming from the branch. And then in the case of zone to hub, this will be, my apologies, zone to hub, this will be a zone that's going to be created on your branch devices, and it'll become basically an egress zone to any traffic going to your hubs, or ingress zone for any traffic coming from your hubs. And I just want to show you a quick setup here. Basically, plugin kind of does the provisioning for this automatically for you. So your zone internal, plugin will create a loopback 901. For your zone to branch, it will actually create your SD-WAN VIF, which we talked about earlier. So SD-WAN 902 in this case, and any tunnels that are part of any of that SD-WAN VIF. And then for zone to hub, this is from a branch perspective. Even though plugin creates it, there's really nothing there that it will add under that specific zone. And then just as a, just as a kind of a second screenshot here, just want to show you the SD-WAN VIFs that the plugin provisions for you. So these are in my environment from, these are my SD-WAN VIFs from the hub perspective. So this is my hub location. I have my SD-WAN 901, which, if you remember, will always be your internet facing SD-WAN VIF. I have 2 internet circuits there. I have my SD-WAN 902, which may or may not be 902. So the naming or numbering scheme may change. It doesn't necessarily have to be 902 always. And that just depends on how often you manipulate the plugin. But SD-WAN 901 will always be 901. These other might actually change. But basically, SD-WAN 902 is my VIF with all my tunnels available going to this branch. SD-WAN 903 is my virtual interface going to this location with only 2 tunnels available. And then SD-WAN 906 is my SD-WAN VIF going to this specific 220 that has 4 tunnels available. So I think I might be running a little short in time here. So let me just check on my portion here. I have about, I'm getting really close to time and we haven't even gotten to demo. I will just skim through these real quickly from SD-WAN login with panorama perspective. Currently, just as an FYI, Cortex Data Lake is not supported for the SD-WAN login functionality. So you have to either have a panorama with in panorama mode, or panorama in management mode with dedicated log collectors. And then I was just going to go over some, there was a question earlier regarding this of some of the overlays and how they're built. So as an example, in the cases where we have a single internet and MPLS, we'll only have 2 tunnels, for example, in this case. But in the cases where we have dual internets, we'll actually have 4 available tunnel paths, because we'll build tunnels between same providers, but then also cross between the providers, right? So for 2 internet circuits, for example, we'll have 4 available paths. If we go to 3 internet circuits, we'll actually have 9 available paths if both sides have 3 circuits, right? And that's basically because in that case, we're building a full mesh of tunnels between the public interfaces. And then just another example, if we have MPLS and 2 public interfaces, or 2 internet in this case, we basically end up with 5 IPsec tunnels for transport in that specific case. So since we are kind of short in time, I'll just go over my quick lab topology I have set up here. And most of the screenshots you saw were from this specific lab. But basically, I have 1 hub, 3 branches, and I have 2 SD-WAN clusters. Branch East and this 220 are part of a single cluster, and then this hybrid NYC is part of a separate cluster. We'll go over some BGP routing overview, SD-WAN VIFs, and then we'll go over some SD-WAN policies and flows and how the failovers work, basically. So I'm just going to stop sharing from this screen, and I will hop onto my lab here so we can see the quick demo of that. Let's see. Stop share. Okay.